In this section, we'll discuss and analyze what are spherical waves. We can write that waves produced by a point isotropic source uniformly in all directions are called spherical waves. We can define if there is a point source which is producing sound in all directions. We can say that sound is being propagated in a spherical region in the three surrounding space in surrounding of this point source. So the waves produced from point source are having wavefronts in a spherical manner. We must understand what do we mean by wavefront. This we define as a spherical wavefront. In some curriculum, wavefront is defined in early classes, but majority of the students are not aware about what do we mean by wavefront. We can also write down what do we mean by a wavefront. It is a cross-sectional plane of a wave in which all medium particles oscillate in same phase. This is a cross-sectional plane of a wave in which all medium particles oscillate in same phase. Like if we talk about a wave propagating in a single direction, then its wavefront will be flat. We can say that this is a plane in which all medium particles oscillate in same phase. Because if it is produced by a source of sound, say here there is a speaker which is producing oscillations. So the wave is carried by the medium and the wavefront propagates with the same speed as that of speed of sound. And it is just a hypothetical plane in which all medium particles we assume that oscillating in same phase. Now if there is a point source which starts or induces oscillations in the surrounding, and say the wave is propagating in the surrounding direction, here we can state all the medium particles which are lying on the spherical surface along which the waves are propagating will oscillate in same phase. So the spherical wavefront will gradually be increasing in its size as the wave is propagating in outward direction. So here we can say the wavefront of a spherical waves is spherical with center located at the source of sound. So if this source is of power p watt, then we can say the power is distributed in the surrounding, in the whole three-dimensional space. If we find out from the source at a distance x at point A, if we find out the intensity of sound at point A, we can say the power p is distributed in the whole spherical zone, which is having the surface area 4 pi x square, because this is a spherical surface of radius x. So we can say the area of the spherical wavefront is 4 pi x square. So this power p watt is crossing this 4 pi x square area per unit time. So intensity we can simply write by power per unit area. So this will be p upon 4 pi x square. So we can say in case of spherical waves, as we move away from the source, intensity of wave is inversely varying with the x square, the square of the distance from the source, and as intensity is inversely proportional to x square, and we know that intensity is proportional to square of amplitude of wave. So we can write for spherical waves, the wave amplitude at any point can be written as inversely proportional to x, because when amplitude is inversely proportional to x, then only intensity will be inversely proportional to x square. If we just write down the equation of spherical wave, we can comfortably write as if there is a point source having a power p watt we already discussed that at a distance x from the source, the whole energy will cross through a spherical surface of radius 4 pi x square. And at this point, the equation of wave we can write as a sine of omega t minus kx, where x here is the radial distance from the point source. And we know that the amplitude is inversely proportional to x. So we can introduce a proportionality constant and amplitude can be written as E naught by x, where A naught we can write as amplitude at a unit distance from the source. So we just substituted here, a wave equation can be written as E naught by x sine of omega t minus kx is the equation we use. Equation of a spherical simple harmonic wave which propagates radially outward from a point source. So there's also a useful relation. I will have some examples based on numerical examples based on the expression of equation of spherical simple harmonic waves, as well as based on the concept of its intensity analysis.